welcome back for this second lecture for this morning. And after exploring various techniques to simulate hydrodynamics on the mesoscopic scale, I'm going now to focus on just one of them, Lattice-Boltzmann. And that's the one that you will play with this afternoon during the practical session. And the outline is as follows. So Lattice-Boltzmann is based on a class of theories that is called kinetic theory. And probably you're not all familiar with kinetic theory, so I will spend a little bit of time to explain what kinetic theory is and rather fast focus on the part of it that is really related to Lattice-Boltzmann. Then I will tell you more in details about the Lattice-Boltzmann method and how you can derive it from the classical and continuum kinetic theory. And after describing the method, how it works, and essentially what you need to understand what you're going to do this afternoon, which will be focused only on simple fluids, I will show you a little bit of what can be done with Lattice-Boltzmann methods, not for simple fluids, but also for complex fluids, that is mixtures, suspensions, porous media, and so on. So first of all, I'd like to come back to the idea I introduced this morning, that if you want to investigate flows, you're not interested in the trajectory of all your solvent molecules, because that's way too much information and that's way too much irrelevant information for your purpose. And what you do, you make local averages of microscopic quantities in order to compute fields such as the density, the velocity, or the mass flux, the pressure or the stress tensor, and the temperature or the energy density and energy fluxes, and so on. If you do this, you lose a lot of information, and sometimes it's sufficient to have just these few fields to describe all the properties of your fluid. Sometimes it's not, and sometimes it can be convenient to step back from this averaging process and simply stop at one level of averaging, which is the description of a probability distribution function that tells you what is the probability to find particles with a given velocity at a given position and a given time. So this quantity f is also a collective quantity, just as the fields, the hydrodynamic fields, but it contains more information than just these fields, because it tells you about joint probability, so to find a particle with a given velocity at a given position and a given time. You can even, in fact, introduce a family of probability distributions where you keep track of two particles, so at two different positions and at a given time. But for what I'm going to describe today, you can simply focus on that single particle density. And the reason it's interesting is that first, from this property, this collective property, you can do a further averaging over the velocities and compute the hydrodynamic variables. So averaging, summing the probability over all possible velocities, you will find the density. And there is a way to compute the other moments. I'm going to come back to that. And the other reason is that it may be a way to introduce other type of algorithms, such as the Lattice-Boltzmann method, that will allow to compute these hydrodynamic variables, but based on this intermediate quantity, that is the one that you are going to evolve and keep track of. So kinetic theory is precisely the theory that tells you how this probability density evolves in time. And just as I've said, the density at a given position can be computed by simply looking what is the probability to find a particle with a given velocity at that position. And then, since you want to know the density of particles and don't care about the velocity, you can simply add all these contributions for all possible velocities. Looking at the second line here, what you're doing is computing the average velocity by weighting the velocity v by the population here that is again this probability distribution. So if you weight the velocity by its corresponding probability and then sum over all velocities, what you get is the mass flux, or the flux, that is the number density times the velocity. But if you have here a mass density, you have a mass flux here. You can do the same thing for the second moment. So take the integral of f v v dv. So that will be a tensor, and that will be the stress tensor. And you can also introduce other moments of this probability distribution function that will give you the energy density, temperature, energy flux, and so on. So it seems that you have not simplified the problem, because now you have a phase space that is larger, because you have 3 coordinates for the position, 3 coordinates for the velocity, and still time. But as you will see later on, it is an advantage. There may be advantages to do so. But let's, for the moment, focus on how this quantity evolves. And generically, variations in this probability density will depend on a number of things. And it can be summarized in that generic equation, which is a kinetic equation, that tells you that f evolves at a given position in time. Then it evolves because of transport. So if you have a flux, then particles will be displaced, and then there will be a change in the probability distribution related to that displacement. So that's the v dot gradient term. And then, because you also have the velocity as a variable in the definition of your probability distribution, you will also have an effect of forces. So if you have a local acceleration, A, then you will also have an effect of this acceleration, but now not involving the derivative with respect to the position of f, but its derivative with respect to velocity. So it's just as a gradient, but now with the coordinates of the velocity. And all this here is related to simply transport within your system. And all the rest is described here by this quantity c hat of f, which is called a collision operator. And it's called the collision operator because it deals with all the interactions within your fluid. So this is very generic, and until you have specified what this collision operator really does to the probability distribution function, you haven't said much. But it's very powerful, and this type of equation was introduced in physics for the kinetic theory of gases by Lattice-Boltzmann. And he introduced in this collision operator here the effect of binary collisions only. So if you have a fluid that is not too dense, you can focus on the effect only of one particle with another. So that won't work for a liquid. But then you can compute what this collision operator should look like based only on the collision section of your particles. And this becomes very difficult mathematically, but you can make some obtain some general results, such as what is called the H theorem. That is, you can build a function of f that can only increase in time or only decrease in time. And that's how Boltzmann demonstrated that even if you have a reversible microscopic dynamics, you can have a quantity that can only increase or decrease in time. So that's very similar to the second principle of thermodynamics, with entropy that can only increase in time. And that was the first microscopic derivation, if you like, that the macroscopic thermodynamics, because F here is a collective quantity, can emerge. So irreversible macroscopic dynamics can emerge from a microscopic dynamics that is reversible. If you want to deal with more complex systems like liquids, then you need to make some further approximations. Just to mention how difficult this problem is from the mathematical point of view, there are many mathematicians working on this, and some of them even won the Fields Medal working on this type of kinetic equations, because it's a very difficult problem from the mathematical point of view. Physicists usually don't bother with this type of difficulties, and they can introduce approximations, solve numerically this type of equations, and make predictions for physical systems. And if the predictions are reasonable enough, they don't care about the mathematical difficulties behind it. So that's what I'm going to tell you about. And essentially what the main effect of collisions is to thermalize your system. So if you have many collisions, it will make this non-equilibrium single particle distribution function towards the local thermal equilibrium. And this local thermal equilibrium is simply the Maxwell-Boltzmann equilibrium. So if you want to know what is the equilibrium distribution of particles at a given position and a given time, it will be proportional to the local density, and the velocities will be distributed according to a Maxwell-Boltzmann distribution. So it's a Gaussian distribution of velocities around the average local velocity u. And u here should be u of r and t. So this is how the local equilibrium looks like. But now you want to relax towards this equilibrium, so you need to specify how the non-equilibrium f will approach the equilibrium, local equilibrium f(x) here. And the simplest form you can imagine is in fact sufficient if you want to recover the hydrodynamic behavior. And the idea is simply to have a linear term that will be so linear in the sense that it's proportional to the difference between f and the equilibrium f. And there is here the inverse of characteristic collision time tau. And as you will see later on, this characteristic time tau is related to the viscosity of your fluid. So this particular form of the collision operator is named BGK from the three people here. And that's what Lattice-Boltzmann is based on. So you have the left term that is exactly this one, and the right term, which is a BGK collision operator that relaxes f towards the local equilibrium value. Now, I told you that that's sufficient to recover the hydrodynamic behavior to use this BGK operator. And one reason is that you will recover the hydrodynamic equation. So the two conservations I've mentioned this morning, namely mass and momentum conservation, by taking the moments of this equation in velocity space. So if we want to have an expression for mass conservation, here we have f, so we want to integrate over all possible velocities. And so we will integrate this equation over all possible velocities. And if we want to have the momentum conservation, we will first multiply by v and then integrate over all possible velocities. So you will see that by doing so, you need to compute the moment in velocity space of the collision operator. And for the BGK operator, it's very simple, because if you integrate f over all velocities, you get the density. But if you take the integral over all velocities of this equilibrium distribution, you also get the density. So the first moment, the zeroth order moment of the collision kernel, is simply equal to 0. If you do the same thing with the first order moment, the first moment in velocity space, by definition for f, it will give you rho u, the flux. And if you take the first moment in velocity space of this quantity here, you can see immediately that you have the first moment of a Gaussian distribution here, and that will give you the average value, so the u here, and then u times rho, the density, is again the definition of the flux, the mass flux. So the first moment of the BGK collision kernel is also equal to 0. So that simplifies a lot when you integrate the kinetic equation to obtain the mass conservation law and the momentum conservation law. And that's how they will emerge, and in particular how the Navier-Stokes equation will emerge from this kinetic equation. So I'm not going to do the full derivation of how this Navier-Stokes equation emerges from the kinetic BGK equation, but I still want to give you a flavor of how this works, because this is, I think, very interesting from the fundamental point of view. It's a very general idea of multiscale analysis. So you know something about the dynamics on a small scale, or the properties on a small scale, and then you want to predict the behavior on a macroscopic scale. So here it's rather simple because it's simply a periodic system. But you could imagine that you have a very big sample, say a few meters, and then you know what happens on the very microscopic scale and want an effective equation for the behavior of your material on the meter scale. So the first thing you need to do is to define the appropriate variables for the small and large scale. So if R here is your position on the microscopic scale, then you will introduce variables that vary slowly on the large scale, and the ratio between the two gives you a parameter epsilon, that is the ratio between the small and large scales. And this may seem a bit mysterious, but in fact, imagine that you're describing your position in meters, in meters on the large scale, and you want to express this position in meters on the large scale as a function of the position in centimeters that you use to describe the small scale. Then the epsilon here would simply be 1 over 100, because you need 100 centimeters to have 1 meter. So there's nothing mysterious about that. It's simply changing the scale you're using to measure positions. Another way to think about this is if you have an absolute position R in the large reference frame, then in a first approximation you can say that I'm looking at a position here using the coarse units, so that would be the slow variables, and roughly speaking you don't care exactly where you are, you just know that you are in this cell, and that's your slowly varying position variable in red here. But then if you want to be more specific, once you know that you are in this cell, you want to know what is exactly your position inside the cell, and that would be the difference between the absolute position and this slowly varying position. So again, that's rather roughly speaking, but that's to give you an idea of what it means to change the scale of your observation. Now, associated with this change in length scale, you also have changes in time scales. And if you have something that moves with a constant velocity, then there will be a time scale related to this drift with a constant velocity. And the relation between this drift time scale on the macroscopic observation scale is simply related to the absolute reference timescale t with the same scaling parameter as for your change between length scales. And if you have a different process than drift, and if you're considering diffusion instead, there will be an associated timescale that does not scale linearly with epsilon, but it will scale as epsilon square, because as you know, the length impacted by a diffusive process scales. So it's the square of this length that scales linearly with time. And you can also think about what the gradient and time derivatives would look like in the other length scale or observation scale. And again, you will have different contributions corresponding to the various processes. And finally, the probability distribution and its moments can also be expanded in powers of this length scale ratio epsilon. So this is very complicated, very tedious, but you can then, starting from your kinetic equation, expand f, the time derivative, the gradients, and your collision kernel in powers of this scaling parameter, and then do an order by order analysis of the different moments in velocity space, and you can show that in the end you obtain mass conservation and Navier-Stokes. So this is tedious, and I'm not going to do it, but I think it's important to understand how the macroscopic equations emerge from the mesoscopic description with a single particle distribution function. Because in practice what we want to do is evolve the kinetic equation numerically and then compute the hydrodynamic observables based on our evolution of f. And this is what the Lattice-Boltzmann method is about. So solving numerically this kinetic equation in the particular case where the collision operator is this BGK collision operator. So how does that work in practice? So I've mentioned that by switching from the hydrodynamic fields, which depend only on three spatial coordinates, and one time coordinate, if you switch to the single particle distribution function, you end up with a 6-dimensional phase space, so 3 for the coordinates, 3 for the components of the velocity, and time. So it seems that you have not gained much because you will have to propagate this quantity in a much higher dimensional space. But it turns out that you can do this efficiently by using just a few velocities to compute exactly the moments that are relevant for the hydrodynamic behavior. So these are just the first two, density and mass flux. But if you choose correctly a few velocities, you will be able to compute exactly these moments. And I'll come back to that idea. But the main point is that you're discretizing your kinetic equation, both in space, by looking only at the probability density on a grid, just as in computational fluid dynamics. And you're also discretizing velocity space by choosing just a few possible velocities for your particles that will be only allowed to move from one grid point to the next during a time step, because you're also discretizing time, as in computational fluid dynamics. So particles can sit only on a grid, and they can only move between time steps from one grid to the next, or grid point to the next. And it means that they had, at the initial time step, they had a velocity that brings them to one of the other grid nodes. And in particular, you can make a good choice of these velocities that allows you to consider only nearest neighbors and next nearest neighbors for the most standard lattices. And with these very few velocities, you will be able to reconstruct the moments. So we, in the Lattice-Boltzmann language, talk about populations. So you have a set of discrete velocities Ci's, and the population corresponds to the value of the probability distribution function at a given point and a given time for this particular velocity Ci. And you can combine these populations by giving them an appropriate weight. And I'll come back to the definition of these weights in a second. But by combining these populations by the appropriate weights, you can reconstruct the zeroth order momentum of the distribution, which is the density, and the first order moment in velocity space. So the sum over all velocities of weights times populations times the velocities, it gives you the mass density, and you can construct the stress tensor using the second moment in velocity space, and so on. So how does that work? Again, you want to compute exactly continuous integrals for a continuous velocity space by a discrete sum. And the way you do this mathematically in general is by using quadratures, numerical quadratures. And because we want to look at populations that will be not equal but similar to the equilibrium Maxwell-Boltzmann distribution that has a Gaussian weight for the velocities, we're going to use a particular choice of quadratures which are called Gauss-Hermite quadratures that precisely involves the Gaussian weights in the Maxwell-Boltzmann distribution. And so these quadratures are defined both by the choice of velocities and the associated weights. So if you specify a choice of velocities, you don't have the flexibility for the weights. They are intricately associated with the set of velocities you have chosen. And I'm illustrating here the most standard ones in 2 dimensions and in 3 dimensions. They satisfy a number of properties. This is why you have not so much flexibility for the design of these lattices. If you want to satisfy that your algorithm in the end is satisfies some important properties such as isotropy and Galilean invariance, you need to satisfy a set of rules for these lattices. And for example, the D2Q9 lattice corresponds to a two-dimensional lattice with 9 velocities, 4 corresponding to the nearest neighbors, 4 corresponding to next nearest neighbors along the diagonals, and the last velocity is simply the 0 velocity because you have some probability not to move between the two time steps. And you see that the weights corresponding to these 3 types of velocities are different. So they have different norms, 0, 1, and square root of 2 in terms of lattice units. And they also have different weights that are related to the norms and the number of these vectors. And the analog of D2Q9 in 2D is for 3D D3Q19s because you have 19 velocities. Again, 0 velocities, nearest neighbors, and next nearest neighbors that connect the center of the cube here to the center of the edges of your cube. And you can also add, if you want, the next neighbors that are at the corner of the cube, and that will give you 27 velocities, again with associated weights. And with this set, so 19 velocities, you can have 3 norms for the vectors, 0, 1, or square root of 2, and you have different weights for the corresponding velocities. So the first thing you do with Lattice-Boltzmann is to choose what lattice you will use, and this implies also the corresponding weights. And from the choice of this lattice, you can then know how to compute the moments of your populations. So briefly, the set of rules that you need to satisfy to impose isotropy and Galilean invariance are a set of lattice sum rules. For example, you want the total probability to be equal to 1. So that's the first one. You want some symmetry on the lattice, so along each direction alpha being equal to x, y, or z, you want this relation between the velocities to be satisfied. And that's obviously the case if you have equal weights for velocities that have same directions but opposite signs. And then you have a third condition that is related to taking the product of components of the velocity vectors, and then this product should be 0 if you are not on the diagonal of this tensor, and it should be equal to a number that is the same for the 3 dimensions along the diagonal, and this number here is the speed of sound square for your lattice model. So this lattice speed of sound is again specific to your choice of lattice, and it turns out that for these two lattices, D2Q19 and D2Q9 and D3Q19, they are both equal to 1/3. So the square of the speed of sound is 1/3 of the lattice speed of sound. So the lattice speed unit, that is the ratio between the length lattice unit and the time lattice unit. So again, the value of 1/3 times this lattice unit for the velocity is related to the choice of weights and velocities. So once you have chosen the lattice, you know how to compute the moments, rho, j, stress tensor, and so on. But you need to evolve these populations in order to predict the evolution of the moments. And to do that, you need to simplify a little bit the BGK collision operator, because here you're doing something that involves equilibrium distribution functions that has a Gaussian distribution in it. And in the end, you want to have something very simple to compute directly the moments. And what you will work with is, in fact, something that corresponds to a linearization of this Gaussian distribution around the local velocity u of r and t. So at any given position and any given time, you can compute the local density and the local velocity, and this allows you to compute the local equilibrium density towards which the BGK collision operator will bring you. You can rewrite it in a slightly different way. So remember, you had m over kBt in the exponential. You can rewrite this introducing the speed of sound, the thermal. So in fact, the thermal velocity, square root of kBt over m, and for an ideal gas, it's equal to the speed of sound. And I'm simply going to refer to the speed of sound for the ideal gas. And remember that earlier this morning, I introduced also this ratio between the velocity and the speed of sound, that is the Mach number. And if you have a small Mach number, you can make an expansion of this Gaussian around the zero average velocity. So we'll have something that looks like a Gaussian distribution times a polynomial in u. And if you take the quadratures here for the equilibrium distribution that you need to compute the collision operator, you will find something very simple. That is that the equilibrium population towards which you want to relax is proportional to the density, just as here, with a weight because we're doing quadratures. And then the Gaussian here, the normalized Gaussian, will give you the low velocity expansion as follows. You have first one that corresponds to no net average velocity, and then something that is proportional to the velocity, and then something that involves the square of the velocity. And you see that it's a very simple expression in terms of both the density and the local velocity, but also in terms of the discrete velocities Ci's. So in practice, if you know the populations Fi at a given node, you can compute the moments here, rho and j, and since j is simply rho times the velocity, you can compute the local velocity u, from which you can compute the equilibrium population towards which you want to relax. And this gives you the final version of the Lattice-Boltzmann algorithm that corresponds to the BGK collision operator. So the transport part in the BGK equation corresponds to this term and that term, and the relaxation part, the collision part, is simply obtained by discretizing the BGK using the discrete time step and also the numerical quadratures for the integral over velocities. So it's very similar to the continuous BGK equation in the sense that you have for each velocity a relaxation of the population towards the local equilibrium. You have here the characteristic collision time in terms of the time step. And this part here involves the population at a given time and a given position. And it will tell you how the population at the next time, but at a different position, will evolve. So Fi corresponds to a velocity Ci. I'll come back a little bit. So if you're looking at a given Fi, you're looking at particles at that position with a given velocity. So if you're looking at the next time step, you will have those particles moving towards that neighboring node, and the population of these particles that on this time step with this velocity will be transported here. And so the population of particles with the same velocity, so that's before the collision, is simply transferring this population onto the neighboring node. So that's why you have a population with the same velocity, Fi, at t plus delta t, but at the neighboring time step corresponding to this particular velocity. So before going into the details of the algorithm in practice, let me first tell you that just as the continuous kinetic equation, BGK equation, gives you the Navier-Stokes equation, you can show that the lattice version of the BGK operator, so the Lattice-Boltzmann, gives you indeed the mass conservation and momentum conservation in the form of Navier-Stokes equation. So you do the same multiple time scale analysis, which is called the Chapman-Enskog analysis. And you can show that the moments, in fact, should be slightly redefined, so the density doesn't change, but the momentum on a given lattice site needs to be slightly corrected. So it's not just the combination of the populations with the velocity and the weights. You also have to correct for a small acceleration on that particular node. And you can guess here that you have this force times delta t over 2, like you would have by discretizing the Newton law of motion in molecular dynamics. And if you redefine the moments or the hydrodynamic variables like that, and there is also a correction for the stress tensor, you recover the evolution corresponding to the Navier-Stokes equation with a kinematic viscosity, nu, that is, again, the ratio between the density, the dynamic density and the mass density, the dynamic viscosity and the mass density. And it's directly related to the parameters of your lattice models, that is the speed of sound square times the unit time step. So you can see that's the square of the velocity times the time. So it is indeed a length squared divided by a time. So it is a diffusion coefficient, as you would expect for the kinematic viscosity. And you see that it also involves some prefactor here with the characteristic collision time here, tau, divided by the time step. And if you have a large time step, a large time, you will have a large collision frequency. No, sorry, that's, I'm confused now. There might be a problem here. If you have a large time, no, that's right, you converge faster toward equilibrium, and so you have a large viscosity. And in the particular case where you relax at each time step, you relax towards the equilibrium distribution, so tau equal to delta t. It's very simple, the algorithm, because then you have this population at the neighboring grid node that is equal to the equilibrium population. So it saves you a little bit of computation. It's less flexible, but it's more efficient. Then also using these two very standard lattices, because then this one is equal to 1/3 in lattice speed units. Then the kinematic viscosity in lattice units will be 1/6 times the units for a diffusion coefficient, delta x squared over delta t. And this afternoon, you will use a code with parameters that are using both the D2Q9 or D3Q19 lattice and this particular choice of collision time. And this corresponds to a kinematic viscosity of 1/6 in lattice units. But again, you can play with this relaxation time to tune the viscosity to model a particular fluid. So how does that work in practice, the algorithm? You have different steps. And essentially, you have one part of the algorithm that deals with transport, and the other one that deals with collisions. So on each lattice node, you have 9 or 19 velocities with associated populations. So on each node, you need to keep track of 9 or 19 numbers. And you want to evolve these 9 or 19 numbers in order to correspond to the BGK equation or the discretized version of it. So you do this in 2 steps. In the first step, you have transport. So I'm just showing a few of these populations, but in fact, on each node, you have 9 or 19 populations. And you are simply going to transfer this number to the neighboring one that correspond to a given velocity. So for example, the particles with velocity corresponding to this velocity will move to the next time step, and the green one moves in that direction, the blue one in that direction. But again, you're moving in all directions at the same time. It's just for clarity. And then you have a collision step. So on the transport step, you're simply moving numbers from one node to the next according to the appropriate velocity. And in the collision step, you're mixing all populations at a given node in order to redistribute the populations. So in practice, what you do is take the population after transport, but before the collision. And from that, you compute the moments, density, mass flux. From that, you can compute the collision kernel, the collision part of the change in populations. And then you simply do this operation to all your populations on a given node. So that will redistribute your velocities. So you had some velocities after transport and before collision, and now you're changing all velocities on a given node. And because you have designed the rules according to the BGK collision operator, what you will end up with is something that reproduces the macroscopic hydrodynamic behavior, so Navier-Stokes on larger scales. And again, you can iterate. So after collision, you do another transport step, and so on. So the Lattice-Boltzmann algorithm has a number of advantages in practice because it's, for example, very easy to implement boundary conditions. And in particular, if you have a solid object or if you're looking at a porous medium, you can simply decide on your grid which nodes belong to the fluid and which one belong to the solid. And then the interface will be somewhere between these nodes. I'll come back to that in a second. You can also introduce different types of boundary conditions. For example, at the end of your simulation domain, just as molecular simulations, you can, for example, use periodic boundary conditions. So whatever was sitting here, maybe that's not a good example, or here, with a velocity in the direction, in the up direction, will enter back in the bottom part of the simulation cell with that same velocity. You can use different types of boundary conditions. For example, you can impose a constant flux at the inlet of your system. So now your system will not be periodic anymore. You impose a constant flux in this direction, and for example, another constant flux that should be equal in total at the outlet of your porous material. At the interface between your fluid and solids, you can implement various boundary conditions. And one of them corresponds to the stick boundary conditions. I told you that was the most standard assumption that you make at a solid-liquid interface. And it's very easily implemented in Lattice-Boltzmann by using what is called the bounce back rule. So if after the collision step you have some particles that want to move inside the solid or across the interface, meaning because you don't have explicit particles, that you have a non-zero population of particles that have a velocity corresponding to crossing the interface. What you do is just before the transport step, you simply take this population and put it, so this number, you associate it with a population of particles on that solid node where the particles would end up, but with an opposite velocity. So essentially what you have done is saying I had particles here moving in that direction with this velocity. I'm just putting back there with an opposite velocity. And therefore, when you go to the transport step, they will move back on the starting node, but with an opposite velocity. And what you have done doing so is imposing a non-slip or stick boundary condition at an interface that lies at the midplane between the plane of a fluid and the plane of solid nodes. So that's something you will also investigate this afternoon in the practical session. You will look at the slit pore and you will have to compare with some analytical results that correspond to a given distance between surfaces, and you will have to remember that the interface lies somewhere in between the fluid and solid nodes. Another interesting aspect of this Lattice-Boltzmann algorithm is that it's very easy to parallelize, and you can do this very easily simply by domain decomposition. That is, if you have a big system, simply cut it into pieces. You can choose whatever shape is convenient for your particular system. And the only communications that you will need between the domains involves the populations at the boundary of your domain, because inside each domain you can do as if the rest of the world didn't exist. So you use the plain Lattice-Boltzmann algorithm, and then the only thing you need to communicate to the rest of the world is the population of particles that wanted to leave towards the neighboring domain, and how many particles, so the populations of particles that want to come back to that domain. So it's a very limited amount of information that is exchanged between the domains, and of course the shape here is maybe not, the aspect ratio here is maybe not very efficient, but if you have a very large system, you can cut it into pieces and have each processor work on part of your system and simply exchange a little bit of information corresponding to the boundaries between domains. So that's exactly how domain decomposition would work for molecular dynamics simulation. But here it's even simpler because you don't have to think about what particles are at the boundary. You just simply know that they are sitting at this, for example, on this layer of nodes, and so on. So by doing this very easy parallelization, you can investigate very complex systems, such as the car I've showed you in my introduction. Here are other examples of simulation of simple fluids, but in a complex flow regime. So you can have a look. Here you have, it's always a flow past the vehicle, but you have a map of what happens to the flow field around this car. Probably this is either the pressure or the velocity that is colored here, but you see that you have vortices here appearing at the rear end of your car or even a turbulent flow behind the bus. And these are, I don't know the details of simulations, but these are apparently done with Lattice-Boltzmann simulations. Another thing I should mention, I didn't do it while referring to boundary conditions, but bounce back is very simple. So you simply need to know if you're at an interface and then do this very simple change in the populations. So you don't have to keep track of a lot of things to implement these boundary conditions. Just for example, what is the shape of the interface. You just need to know where the solid is and where the fluid is. And then with this very simple rule, you can implement non-slip boundary conditions, whatever the shape of the interface. So that's very useful if you have a complex shape like here or there. Do you have any questions about simple fluids?
Yes. I have a naive question. When you're displacing one particle from a node of your grid to another one, as far as I understood, you don't check if it's an empty node, which surprises me.
So I didn't want to go into the history of lattice methods, but in fact, Lattice-Boltzmann was derived from another method that was called the lattice gas automaton, where instead of having populations at a given node, so that is simply looking at the number, so a discretized version of the single particle density, you would have explicit particles on the grid. So a site could be either empty or occupied by a particle with one of the 9 or 19 velocities. And the information you need to keep track of is then just a number of zeros and ones. It's 0 if you have no particle at a given site, and then 1 if it is occupied with particles that has one of the lattice velocities. So you can use a discrete algorithm that also has collision rules, and it will in fact correspond to moving particles just as in Lattice-Boltzmann and redistributing particles with rules that you can cook not from a continuous kinetic equation, but with whatever physical sense you have on how the collisions occur. It will be only binary conditions because you cannot have more than one or maybe two particles before the collision. So in fact, you have essentially a grid that is mainly empty, and sometimes you have a few collisions. And then what you do in this scheme is average. So take a node and then average over time what is the density of particles with a given velocity. So we'll have 0, 0, 0, sometimes 1 with a given velocity and so on. And then you make an average over time, and it will tell you what is the population at that given node by looking at the average of integer numbers. It turns out that it's not very efficient to do it that way, and you can in fact do better by simply considering, instead of discrete, so integer numbers, working only with real numbers, so that correspond really to the discrete, the value of the population for a discrete set of velocities, and use quadratures to derive the discrete algorithm from the continuous one. But it's not, historically, that's not how it was invented. It was made of discrete particles that would indeed collide with each other, and then you would have to take care of whether the site is occupied or not. Right now, what you're doing is simply working with a probability distribution that is already an average quantity, and then you're looking at how this average quantity evolves in time. So you don't, this schematic here is useful in terms of thinking at what you're doing to the numbers, but you don't have explicit particles living on a lattice. You have numbers that correspond to the probability of being somewhere with a given velocity. Does that answer your question? Any other question about simple fluids? Yes?
About your grid, can you imagine to have irregular patterns?
Yes, so yeah. So most algorithms would work with the lattice I've shown. So lattices I've shown, very regular. Nowadays, it's possible to make irregular grids, but then you have to think much harder about the weights corresponding to each velocities and how to compute the moments from the velocities, but it is nowadays possible. Yeah. Another thing about the lattices, if you want to compute exactly the density and the momentum and the stress, it's okay to use these lattices. If you want to compute exactly the thermal flux, using 19 velocities will not be enough, and you will need to work with, or okay, if you want to compute exactly higher moments, more generally, if you want to compute exactly higher moments of the velocity distribution, you will need to have higher order quadratures, and that means using more velocities in your lattice. But that's also doable. So if you have simulations that work with constant temperature, you don't really care about using more velocities. But if you're looking at thermal gradients, then you need to be very careful about what you're doing. Any other question about simple fluids? Okay, so now briefly, I'm going to show you a few examples of things that can be done when you have more complex fluids. For example, working with binary mixtures or ternary mixtures, or when you have particles, a mixture in a porous medium, or when you have particles with a mixture. And the way to do this depends on the system you're looking at and the problem you're looking at, but also it's a matter of choice because you have several strategies to do this. The first one is to associate to each species a set of populations. So that would be 19 velocities for water, 19 velocities for oil, and do exactly the same kind of propagation for both types of species. So that would be a pure Lattice-Boltzmann approach. The other way of thinking about mixtures is to have a fluid density with a population associated with density as a whole, with something that will give you the total mass and total momentum density when you integrate over velocity space. And then you introduce the binary or the multi-component nature by using a local composition field that will, for example, vary between 0 if you're in water and 1 if you're in oil. And then you have some special way to couple this composition field with the Lattice-Boltzmann algorithm, and that's a more hybrid approach of these complex systems. And the essential part in how you do the coupling is how you capture the interactions within your fluid and your mixture, and how this local composition will have an effect on the local interactions and in turn on the local force acting on your fluid and on the local changes in composition, so the fluxes in each type of species as a function of the local composition and the gradients in the local composition. And the way you usually do this either from a proper thermodynamic model or based on simplified thermodynamic models that were introduced initially in this type of methods. The way you do this is to compute the local force acting on the fluid that enters in the Lattice-Boltzmann algorithm based on chemical potential gradients. And the idea is that if you have a local composition variable, say the local density in each species, then you can compute the free energy of your system as a functional of these composition fields. And then the chemical potential. So if you have a free energy model for your free energy as a function of the density in each species. So alpha would be the index for your species in your system. Then you can compute the chemical potential of each species locally as a functional derivative of this free energy functional with respect to each composition variable. And that would give you the value of the local chemical potential. And once you know the local chemical potential, you can compute the force acting. So let me use a different F for the free energy and for the force. You can compute the local force based on the local chemical potential gradients. And that's nothing but the Gibbs-Duhem equation. That you know from thermodynamics. So based on your free energy functional, so that's your model of how the free energy depends on the local composition, you can compute the local force acting on your fluid. And that you can inject in the Lattice-Boltzmann algorithm. So I'm showing here one example of Lattice-Boltzmann simulations for the decomposition of an all-water mixture. So you have color codes with blue and red for the two components of your mixture. Then you start from something that is initially almost homogeneous, but with some random perturbation. And because oil and water don't want to mix, because you have some interaction. So for example, your free energy model would look in that case as as a double well as a function of your composition parameter. So initially, you start something close to an average composition, and the system wants to phase separate and fall everywhere into one or the other basin corresponding to one or the other phase. And if you do this Lattice-Boltzmann, or if you do this this simulation of the phase separation by incorporating the gradients that come only from diffusion, so you will also have fluxes for both species that come from the diffusion due to the local chemical potential gradients, this will look like this. So you have domains that will grow with a size of the domains that grows diffusively, because you do not capture something that will appear obviously in the next video that I will play in a moment. It is the fact that you're creating interfaces, and because you have interfaces, you have interfacial stresses that correspond to these local forces, and this interfacial stress will drive the fluid at the interface, and it will accelerate the fluid at the interface, and so it will modify completely the dynamics of your fluid. So you see first that it goes much faster, and that you phase separate, that's approximately the same time scale. It phase separates much faster, but it also has a completely different dynamics at intermediate time scales. And if you've looked at how your vinaigrette demixes, or if you just look at an oil droplet when you're cooking pasta and start stirring it, probably you have found that it looks much more like the one that captures these interfacial stresses. Another example of a complex system is that of a mixture. So you don't see here the underlying fluid of oil and water, but you also have in this mixture different particles, colloidal particles, that have different properties with respect to water and oil. And I'm going to play a movie in a second, but what you will see is or are surfaces, complex surfaces that materialize the interface between oil and water that you will not see. And again, that's done with Lattice-Boltzmann simulations. So the colloidal particles moved because you have an underlying fluid that moves. And the particles tend to stuck at the interface. So the blue and yellow surfaces are the interface between water and oil. And you see that at some point you completely phase separate, and you tend to accumulate the colloidal particles at the interface, and at some point it becomes stuck. So it forms a gel or a glass. And the dynamics is very complicated, and it depends a lot on the dynamics of the underlying binary mixture. Another example of complex systems, porous media, and you will play a little bit with porous media this afternoon. Not with binary mixtures, but with simple fluids. If you have binary mixtures, you also need to think about surface thermodynamics, just as I've mentioned for the colloidal particles. You can impose specific rules that also involve the local composition, and you can design these rules in order to impose, for example, a given wetting angle between your solid and your fluids. You can also impose specific hydrodynamic boundary conditions. For example, if you have water and oil on a hydrophobic surface, they might behave differently, not only in terms of wetting, but also in thermodynamics, but also in terms of dynamics, so slip or no slip. And another thing you may want to do if you have a porous material, if it's not rigid, you can also try to model the coupling between the fluid and the solid by introducing discrete elements for the solid, just as for the colloids. And then you will need to think about how the fluid pushes the solid or exerts force and torques on the solid particles, and also how the solid acts back on the fluid. So I'm going to show you two videos that you can find on YouTube. One is called, corresponds to a situation called drainage. So initially, you have a porous material with solid objects that are the black dots everywhere, that is filled with fluid which is colored in blue. And then what we're going to do is to push another fluid from the side, and it has a different color, and you will see how the second fluid progresses through the material. And you see that you have to push the fluid, but you also have to satisfy some constraints at the interface with the solid, and you have some contact lines between the three components, solid and the two fluids. And you see that you can have very complex patterns generated by this simulation method. And you can also access very different hydrodynamic regimes. For example, this one corresponds to one particular ratio between capillary effects and advection, but you can push much faster, and you will see that you have different shapes for the fluid patterns inside the material. Second video is for a single component fluid, but now with a moving solid. So essentially what you're simulating here is two piles of sand, and the sand is modeled with disks, and you can see how the disk rotates by following, when they are in blue, the lines that can help you visualize their orientation. And you see that as the flow progresses, you will generate torque and force on these disks, and you might even push them away. So you can model erosion using this type of simulations. Again, this requires thinking about how you couple your discrete solid elements to your Lattice-Boltzmann fluid. And final examples that are pretty fun, but to be honest, I don't know how they have been made. I found the videos on the internet, and they say it's with Lattice-Boltzmann. I'm pretty sure you can do it with Lattice-Boltzmann, but I have no idea about the details. But just to show you that you can simulate very complex systems, here you will see the boiling of a fluid. So you have a non-thermal Lattice-Boltzmann. You need to use a non-thermal Lattice-Boltzmann, and you impose a large temperature on the bottom part. And then this will induce a phase separation just like that at the boundary. And then because you also have a gravity field, I guess, in this direction, and the gas phase will be less dense than the liquid phase, and then you will have a rise of the bubbles. So they are generated by a phase separation in the bottom part, but then they rise due to buoyancy. And all this can be captured by Lattice-Boltzmann simulations. And finally, this last video, you will see a simulation of combustion. So again, this involves non-thermal simulations, but also some chemical reactions that probably also dissipate energy. So here you have a flame, and then you're generating smoke, and you see that you have a turbulent flow of the smoke, and because it's a closed cavity, you have some swirls, and at some point you see that swirls here will displace the region where fire burns, and you can generate very complex patterns and flow patterns based on this type of simulations. Again, I don't know the details about how this is done, so I know that it is possible to do it with Lattice-Boltzmann, but I cannot tell about this specific simulation. Okay, so before some last words about what you're doing to do this afternoon, do you have some questions? No? So you may ask more questions this afternoon. So what we wanted to do this afternoon is to familiarize you with the Lattice-Boltzmann method, and you're going to use a code that we're developing here in Paris. And obviously, you want to start with simple fluids in simple geometries, because that will give you a flavor of what is important, how to choose the parameters, simulation parameters, and are the assumptions that we've made to derive the Lattice-Boltzmann algorithm justified in the conditions you're going to simulate. And so we'll start with a Poiseuille flow that I've already mentioned. So two parallel walls, infinite walls, a uniform fluid, and a uniform pressure gradient in one particular direction. And then after some steady state that you will look at, you should end up with the final steady state. After some transient state that you will investigate, you will find a steady state that has a parabolic velocity profile. And because we have a simple analytical solution in that case, and you will have to find that solution in the first minutes of the practical session, we'll help you with that if it's complicated. You will have some analytical reference to compare with, and this will help you understand the influence of discretization, think about the timescales corresponding to the transient regime, so how long does it take the fluid to establish the steady state, and so on. And that's steady state is, of course, much more difficult to do analytically, but that's very simple, simply propagating the Lattice-Boltzmann algorithm. Then once you are a bit more familiarized with code and the method, you will have the opportunity to play with porous media and look at properties such as the permeability, which tells you essentially how the flux is proportional to the applied pressure gradient. And you will have a number of geometries to play with to look at how this permeability depends on how the obstacles are dispersed in your material. So this will be a model of a simple model of a chromatographic column. And finally, and probably that's maybe the time you will want to spend more time on, we will give you some tools to generate your own systems simply from letters or from signs. And you can generate your input files for the Lattice-Boltzmann code very easily. And then you can play with applying pressure in these toy models. And you can, I'm sure you will have some fun doing that. Okay, so I don't know if I should stop here. Marco, you want me to do the analytical calculations first, or?
As you want. If you want to anticipate something, or
I think we probably should stop here and then start with the analytical calculations together at the beginning of the practical session.